Oke,
Good morning, you can start.
please give me to share my screen. Oke, Assalamualaikum warahmatullahi wabarakatuh. Selamat siang kepada bapak-bapak, ibu-ibu, teman-teman, adik-adik juga semuanya dengan acara webinar atau kuliah umum PT Testindo bekerjasama dengan Universitas Kuala. Ini adalah webinar kelima yang Testindo laksanakan untuk tahun 2020 ini. Selama pandemi ini kita beraktivitas untuk tetap di rumah dan sharing informasi teknologi terkait bidang asesmen pengujian di teknik sipil. Terima kasih kepada perwakilan dari Unsia. Nanti ada dari beliau dari Pak Surya Bermansyah, terus Pak Yusria juga yang akan nanti menyampaikan kuliahnya, pembukaan acara ini. Sebentar. Oke, saya akan sampaikan beberapa hal yang bermanfaat untuk kita semua. Sebelum kita memulai topik untuk pengujian tiang fondasi file testing, ini adalah tahapan pelaksanaan asesmen evaluasi struktur, baik itu struktur beton, berbasis beton atau baja, jembatan, gedung, dermaga, atau struktur lainnya. Tahapan ini dilalui dan menjadi satu kembali ke sini untuk semua prosesnya, dari mulai pemeriksaan detail visual, lalu kita perlu memeriksa geometri dari bangunan tersebut. Di sini kita perlu nanti akan menghasilkan S-build drawing yang akan kita modelkan nanti. Di sini ada beberapa tool yang bisa kita gunakan. Lalu ada pengujian mutu dari bangunan tersebut, materialnya ada yang berupa beton, ada yang baja, ada yang di struktur, ada yang di pondasi, ada yang di struktur atas, ada yang di pondasi, dan juga kita untuk beberapa kasus yang misalnya terjadi penurunan tanah, misalnya penurunan kemiringan bangunan, kita juga perlu mengambil data tanah. Di Indonesia sendiri ada data-data, ada SNI 8460 2017 untuk pengujian alat-alat pengujian tanah, di sana ada listnya. Dan dari sini semua nanti kita akan olah dan analisa dengan pendekatan simulasi permodelan untuk tahu kapasitas struktur. Dan untuk membuktikan, mengkonfirmasi analisa kita, maka kita validasi dengan loading test. Loading test adalah pengujian dengan menggunakan beban-beban dan sensor. Untuk pengujian statis, itu kita biasanya menggunakan pengukuran regangan, pengukuran rendutan, dan dinamis ada pengukuran getaran ya, untuk frekuensi pribadi. Nah, nanti kita dapatkan kesimpulan dari sana. Apakah perkuatannya berupa metodenya apa, RAB-nya apa, dan biasanya konsultan akan memberikan gambar juga. Nah, untuk semua proses di sini, Testindo provide semua peralatan-peralatan ujinya, peralatan-peralatan asesmennya. Ada asesmen yang memang dilakukan secara destructive test, ada yang digunakan metode tidak langsung atau non-destructive test. baik itu pengujian di lapangan maupun pengujian di laboratorium. Jadi Testindo menyediakan peralatan pengujiannya maupun bagi klien yang juga beberapa yang sudah kami undang di sini, kami juga melayani jasa untuk pengujiannya juga, selain menjual alat-alat pengujian. Nah, ini bentuk-bentuk alat-alat ujinya. Nah, topik kita siang ini, pengujian tiang fondasi, kita akan disampaikan di sesi ketiga. Saya kasih pembukaan sedikit, bahwasanya pengujian tiang fondasi ada 2 tahap, yaitu pada masa konstruksi dan pasca konstruksi. Pada masa konstruksi, pihak kontraktor yang telah membuat tiang-tiang biasanya seperti di gambar-gambar ini, fondasi-fondasinya itu dites ketika setelah dia memancang. Nah, ini contoh pengujiannya. Ada pengujian yang standar di kita, ada PDA misalnya untuk daya dukung tiang, lalu ada pile integrity test, close hole sonic logging. Nah, ini akan kita bahas pada di antara yang kita bahas oleh Mr. Joram Amir dari pile test nanti. Dan static load test ini adalah untuk dasar penerimaan dari pekerjaan kontraktor, apakah masuk kepada spek yang disepakati dengan owner atau tidak. Lalu untuk asesmen, biasanya ketika bangunan ada pengubahan fungsi atau bangunan telah mencapai umur 10 tahun, itu wajib di asesmen. Di antaranya asesmen itu juga termasuk sampai ke fondasi. Nah, yang biasa kami kerjakan dan alat tersedia di lapangan diantaranya adalah paralel seismic instrument. Ini peralatan terkait juga dengan ilmu geofisika, gimana kita mendapatkan gambaran dari si tiang itu, apakah utuh atau ada kerusakan. Lalu ada geopenetrating radar. Kita juga sama untuk dapat geometri seperti gambar yang di bawah ini. Ini adalah hasil dari georadar yang diolah. Jadi georadar ini adalah alat untuk men-scan, seperti kita men-scan bayi di perut ibunya itu. Tampilannya bisa diolah nanti untuk menampilkan bentuk dari fondasi. Seperti ini ada filenya, lalu ada kedalamannya berapa. Ini bisa didapatkan dengan menggunakan georadar dan parallel seismic instrument yang untuk pasca konstruksi untuk asesmen. Nah, saya perkenalkan juga speaker kita, Mr. Joram Amir ini. Beliau lahir di negara Israel. Ini sekolahnya, dan beliau punya keanggotaan profesional di banyak organisasi internasional. Ini adalah CV beliau. Saya slide di sini. Lalu pengalaman dia dari tahun 65 sampai sekarang dia punya perusahaan Amir Technical Engineering. Lalu juga sabbatical as corporate consultant. Jadi beliau ini memang basicnya geoteknik, dan dari banyak paper-paper yang publikasi yang beliau punya di sini, beliau adalah peneliti yang akhirnya berinovasi menciptakan produk untuk pengujian yang sekarang dia punya perusahaan namanya PLTest ini. Oke, itu dari Testindo pembukanya. Selanjutnya kami silakan kepada perwakilan dari Unsiah, waktu dan tempatnya kami persilakan. Dengan Pak Surya ya Pak ya, dengan Pak Yusya Dharma ya Pak ya.
Mungkin saya akan sedikit sampaikan, kemudian dilanjut oleh Pak Yusya. Pak Yusyanya, ya. Ya. Terima kasih Assalamualaikum warahmatullahi wabarakatuh. Saya mewakili Ikatan Alumni Sarjana Teknik Sipil Kuliah, ya. Mengucapkan terima kasih banyak kepada yang mau berbagi ilmu, update informasi kepada aplikasi katakanlah dengan sedikit dan juga jurusan dan seterusnya memberikan informasi itu, berbagi informasi kepada mahasiswa kami tentunya nanti akan disampaikan oleh Pak Yusuf ya. Informasi-informasi ini penting bagi kami di daerah di Aceh agar pengetahuan tentang konstruksi di lapangan ya di proyek-proyek yang dikerjakan oleh kita di Aceh ini juga dapat bisa mengikuti update perkembangan teknologi pengujian yang ada. Mungkin itu saja dari saya singkat. Mungkin akan dilanjutkan oleh Pak Yusuf dari kampus. Demikian Pak Zul. Assalamualaikum warahmatullahi wabarakatuh.
Salam, betul. Mangga Pak Yusria, silakan Pak. Hello, enough. Please give a speaker for Mr. Yusria. Enough. Suaranya belum kedengaran Pak Yusria. Udah Pak. Mangga Pak.
Silakan Pak Yusuf.
Mr. Dharma, you can speak. So, Zulfkri, whose turn is it?
Pak Yusria, silakan Pak.
Sorry, we cannot hear you.
Kayaknya sinyal mungkin Pak Surya dari kantor Pak Yusria mungkin bisa tes suara Pak Surya, Pak Yusria. Memang besar ininya mungkin ya. Pak Yusria tadi kedengaran Pak Yusria tadi. Hilang datang hilang.
Hilang timbul Pak ya.
Udah Pak. Alhamdulillah nih.
Sudah.
יכול להיות שהוא ניסה לדבר, שומעים.
אפשר לדעת כמה משתתפים יש לנו
כן,
עכשיו?
יש 122.
כמה?
122.
לא, בינתיים זה לא...
זה...
מקווה שלא ברחו.
לא. לא.
אבל אני רוצה עוד פעם לכוון שזה שם, אמרתי עליו?
כן.
תגיד לי, איך בדיוק אתה רוצה את זה? אני...
לא, אז פשוט שהיא עליו, אם אפשר. אבל יכול להיות שהיא קולטת אותם. Zulfkri, so are we moving?
Yes, please. No. Mister,
So Zulfkri, are we moving on?
okay, please continue.
To Mr. Amir? Okay, thank you.
Oke, karena gangguan sinyal, teman-teman, kita lanjut ke acara. Terima kasih kepada Pak Isir dulu sama Pak Kuliah mewakili Unsiah. Mudah-mudahan sama-sama bermanfaat ya acara kita. Mr. Joram, please your speech. Start.
Like dinosaurs. Why delicious.
להבנתי, כדאי שתתחיל. כן,
Ena, please start with Mr. Joram.
אפשר להתחיל?
כן, רגע.
Good afternoon, everybody. Thank you for joining us today. During the next hour or so, we are going to discuss the subject of pile integrity testing. This is quite an important subject, which very few civil engineers know anything about, for the simple reason they don't teach it in the university. So I hope that after this hour or so, you will know more about pile integrity testing than your professors know. Okay, let's start. During this presentation, I'm going to discuss types of deep foundations, defects in deep foundations, pile integrity testing by direct methods and indirect methods, and to present the BIT, testing pile verticality, PSI, testing hidden piles. We are going to devote a few minutes to the subject of anomalies, flaws, and defects. These are terms that are often mixed. And I hope we'll have time for questions and answers and some concluding remarks. Pile is a slender, deep foundation, either prefabricated or cast in situ. Piling are very old. Wooden piles have been discovered in London and dated to be more than 4,000 years BC, which means more than 6,000 years old. This is really old. Today, we have many kinds of deep foundations, piles of all kinds. Generally, we divide them into displacement piles and replacement piles. But there are many pile types, and contractors all the time develop new types of piles with sizes growing larger and load carrying capacity growing higher and higher. All of piles have one thing in common. The final product is invisible. It looks like this in many cases. Now we have to eliminate the guesswork and get as much information about the hidden part of the pile. And the hidden part is sometimes very bad looking, like this example, piles that have been exposed and do not show very good workmanship. Here the contractor was a little smarter and used casings made out of cardboard pipes, and you see that this was not enough. Still, there are defects in these piles. This is a pile produced by a very good contractor, but unfortunately, unknown to the contractor, he hit a live sewage pipe, and this is the result. Poor pile. This pile was produced by a contractor who was not so good. He used polymer slurry, but probably not very successfully. Here's a diaphragm wall cast with bentonite. Also, the result not very positive. Another wall, even worse. This wall has huge cavities inside, and of course, this is very unsatisfactory. Here is a pile cast under excellent conditions. Only when the contractor concreted the pile to this level, the concrete supply was finished. So he delayed the rest of the work to the next morning. During the night, there was some wind that blew some sand, and there was no contact between the two parts. Now the owner is very happy. He got 2 piles for the cost of 1. Another example, ideal conditions for drilling, hard clay, no groundwater, and still result unsatisfactory. So you see that piles may have many forms of defects. Like this one. Here, the pile is more or less intact, but the outside skin is exposed. And of course, with time, the reinforcement cage can be corroded, and the pile will lose most of its serviceability. The same thing from close up, not very satisfactory. How many piles can be defective? It depends on the method, on the time, on, of course, the most important question, who does the testing? The first figures we had in literature said that 1.7% of the piles had defects. But of course, at that time, that was about 40 years ago, the equipment was very poor, very primitive, and tests were performed by the contractor who produced the piles. Of course, he was not very happy to report piles that were borderline case. Later on, California, they use a lot of radioactive testing. They found that among almost 3,000 piles tested, 20% had flaws, 600 out of 3,000. That's quite a lot. Visual inspection is even more severe. Values of 64 or 76% of files with flows. In Asia, visual inspection produced more than 20% float files. Italy, ultrasonic testing, 12%. Israel, 22, 65%, 43%. These figures are alarming. And the conclusion is that we must find a way to check the files and find their integrity before we start loading them with the structure. File integrity means meeting the requirements with regard to material and geometry. The requirements are summarized in the drawings and in the specifications. And if we don't meet the requirements, the file integrity is poor. Flows can be in the material, like poor concrete, not far from the top of the pile, or soft bottom, concrete that is mixed with mud, drilling mud, bentonite, and so on. This is poor material. And we can have abnormal geometry, like a short pile. Short pile can be caused because of soil collapse or because of greed of the contractor, who hopes that nobody will ever catch the fact that his piles were too short. Necking. Necking happens when there is a soil collapse during concreting of the pile. And here we have a pile that is probably intact, but is climbed. It's not vertical as it should be. This is also a question of integrity. Integrity testing techniques are used to discover defects before they can cause any damage. In a very famous case in Hong Kong, float piles were discovered only when the superstructure reached the 30th floor. By that time, the building started to settle so much that it had to be abandoned and torn down. So our ideal is to discover the defects before they can cause any damage. We have two general methods of integrity testing. The first of all is direct methods, excavation. If you suspect that the top of the pile is of poor construction, you can just excavate around it. Of course, the depth is limited by the means you have, the excavator, and by groundwater. The second method, which is almost not unlimited by depth, is core drilling. We can core drill in the pile and see what kind of concrete we have inside. Core drilling can be performed to larger depth, but of course it will give you information only about a small percentage of the cross-section of the pile. Other methods are indirect. We can use long wave, like the PET instrument that I'm going to present to you soon, and short wave, the CHAM. Long waves can travel in the pile only up and down, while short wave, like that mouse, can travel up and down, sideways, and in all other kinds of directions. That's the difference between the two main testing methods. The sonic method, פה היה לנו סרטון שנעלם.
כן, אבל לא פליי.
אין סרטון?
לא, זה בא מהמצגת.
המצגת, קליק על זה?
לא, תלחץ על זה.
זה היה פה. The sonic method uses the long wave. we hit the pile with the hammer, and the sensor, which you see here, receives the reflected waves, and by the picture we get on the screen, we can determine the pile integrity. The principle of the method can be seen here with the pile wave program. This software is freeware from our website, and it simulates the long wave test. זהו, אני לא יכול להפעיל פה שום דבר מהרשת. חבל.
אז אתה רוצה שאני אנסה מהמחשב שלי? אוקיי.
Okay, just a moment.
הוא אמור לשתף, ומשום מה לא מראה את הסרטון.
במחשב שלו זה גם לא מראה, זאת אומרת, יש פה ממש
בסדר.
המחשב שלי כולל את ה...
כן, אבל למה זה לא מתחיל את הסרטון?
שאלה טובה. יש משהו שאפשר לעשות מהר?
לי יש את אותו דבר. שאלה אם אני יכולה... כן, אני אנסה.
שפלי את המצגת שלה.
אני לא מה...
בסדר, אבל...
אתה רוצה לחבר...
לא קשור,
אני יכול להציג את זה עכשיו. את הסרטון.
כן, אני...
אתה חושב שאתה יכול להציג את זה?
את הסרטון אני יכול...
עובד לך סרטון במחשב?
במחשב שלי כן.
אז סבבה, אני יכול להציג את זה, כן.
אבל הוא צריך להיות מחובר. טוב.
אתה יכולה להעלות אותו בתור פרזנטור, לא?
כן, פרזנטור שלו.
Just a moment, we'll solve the little problem very soon, I hope.
תגיע ל-25, זה שקוף.
אצלך גם לא עובד המצגת?
אני לא בדקתי את זה, אבל היא עובדה לי עד היום. הנה, פה זה עובד.
תחברי המחשב שלך את הכבל. את רוצה?
כן, אפשר.
עדיף, בואי אפשר לחבר את ה...
אצלו
זה כבר עובד. הוא מציג?
כן.
לא יודע אם שומעים.
אפשר לתת full screen?
זה הכי full screen שיש.
עינת, תחברי את המחשב הזה למערכת, בבקשה.
שומעים אותך, את לא יכולה לדבר.
Okay, here we have a pile that we have to test by the PET long wave method. Here's the sensor, we press it against the top of the pile, and we hit it lightly with a plastic hammer. We don't have to hit very hard. The wave produced by the hammer blow goes down all the way to the toe and then returns to the sensor. The result is shown on the screen. Now imagine a pile that has a defect here. When the wave reaches the defect, it is reflected back and part of the wave goes down to the toe. On the screen, we can see not a straight line, but a line which goes down and then up, which means that we have a necking here. אני יכול לחזור? עכשיו את הפייל וייב. גדי, אתה יכול לעלות?
רגע, אני אנסה.
Now we'll just have a quick look at the pile wave program. Here you see a straight pile, and you see the wave, compressive wave is the green one that goes down from left to right to the bottom of the pile and returns to the top. Can you choose one with a defect on the left?
Yeah, I can make one.
Top left.
And here.
Local. Halfway local. Right. Here we have a Okay. Here we have a pile that has a bulging, a larger cross section in the middle. You see that the waves are returned from the bulging as well as they return from the toe. I hope that after this lecture you'll go and play a little with the software and learn how the method works. Here are some real examples from real piles. אפשר להעלות אותי עכשיו?
אז עכשיו אני אשדר, כי עברנו את זה למחשב שלי.
Sorry for the slight delay. שמתחיל לדפדף.
לא, אני יכולה לעשות את זה. צריכה שקופית 26.
כן. אפשר לרדת? אוקיי. כן. אני עדיין לא בתמונה.
לא, אז הוא יעבור משקופית דרכי מהמחשב שלי.
אפשר להעלות את המסך שלי?
אז תני לו את הכבל, פשוט אם יש לו בהם הסרטון, אז
לא,
הוא יכול
צריך
להציג.
לעבור משקופית לשקופית.
אז שתחברי אותו שוב פעם, עם הכבל הזה של השאר, שיעבור שקופית לשקופית.
אוקיי.
לא הולך?
Okay, here we see an example of a result from a good pile. You see that on the left we see the hammer blow. And on the right, the reflected wave arriving from the bottom at a depth of 10 meters. So no bad.
אז אולי שיעבד מהמחשב שלי, או שאני אעבד.
שנייה.
תנסי להעביר.
לא חיברת טוב. הנה.
היא לקחה את זה.
אני כרגע הפרזנטר. כי אני...
זה המחשב אצלו פה. מה את רוצה? שזה המחשב? זה או השני?
אוקיי.
אני העליתי את זה מפה. טוב, בוא ננסה.
כן. אבל הוא לא מציג את המצג שלי.
אז שהפרזנטר אצלי עכשיו. כי אני העליתי את זה.
את רוצה לחבר את זה אצלך את הכבל?
אני רוצה שאפשר יהיה להעביר את השקופיות. אז אם אני
אוקיי,
עושה...
חברי אצלך. את לא יכולה להעביר אותו לפרזנטור שהוא יעביר אצלו. ואז הכי טוב שהוא יעביר אצלו.
רק שנייה.
הם עושים את הפרזנטר.
בדיוק.
אני לא יכולה, כי הוא פאנליסט, אבל הוא אמור רק כשהוא עושה share, אז הוא יצא.
טוב, אז תעביר את זה אצלך.
קח את המחשב שלי. שאם אתה רוצה שאני אעביר משהו. להעביר שלוש.
Okay, here we see examples of three tests. The top one was performed on a good pile. The central one is a test on a pile that has a necking in the middle. And the bottom one is a pile that has a large bulge below the middle. The PET has a utility for signal matching, and when you enter the shape of the graph you got from the system, you can, by iteration, find an approximate shape of the pile. You see that this is the pile that has a large bulge, and you see the graph, or what you call the reflectogram, showing the rise of the line. The sonic method, or the PET, can find many things. First of all, the length of the pile, approximately, to within an accuracy of 5 to 10%. We can find inclusions of foreign material, like mud, drilling mud, etc. Horizontal cracking. Joints and stage concreting with a break in the middle. Changes in the cross-section. Abrupt changes, not gradual changes. And changes in soil layers. This is a problem that affects the results, and we have to take it into account. The method cannot find anything when the pile top looks like this. This is a hopeless case. Of course, you have to clean the top quite well before the testing. Advantages are quick. The test is very quick. It's inexpensive. It's universal. It applies to concrete piles, wooden piles, some steel piles, etc. And there is no pre-selection. You don't have to make any special preparation except for cleaning the top. The test effectiveness is limited by the slenderness ratio, not by the length, but by the ratio between the length and the diameter. A pile that has a very long or very large slenderness ratio is more difficult to test and get a toe reflection. The test duration, I said that the test is very short. Within 30 seconds, you can test 60% of the piles. Within 90 seconds, you can test about 90% of the piles. So the test is very quick, and therefore it is also very cheap, inexpensive, which means that you can afford testing all the piles on a given site. Now, when is this test inapplicable? Or when does it provide results that are not good enough? If we have a large pile with heavy loads, the test doesn't have enough resolution to satisfy our needs. If the pile is not cast to the top level, or the ground level, sometimes if you plan to excavate a basement after casting the piles, in this case you cannot use the method because you cannot approach the top of the pile. If you have a pile in a mountainous, rocky terrain, and you drill in the rock, you have a very nice straight profile. But if you have rock fill above, the cavities in the fill are filled with concrete, and you have a very rough profile, which makes the testing impossible to analyze. And of course, if you have a wall, the method is good only for one-directional elements and not for walls. In this case, we use the cross-hole ultrasonic testing method, or the CHAM. For the CHAM, we need a number of access tubes cast in the pile, at least 2. The instrument and the computer, 2 two pulleys, cables with sensors, and when we pull both the sensor to the top of the pile, they can discover all defects that are in between. How is it done on site? On this site, we have 12 piles that we are going to test by the cross-hole testing. Here is the CHAM instrument and the computer, depth meter, and we put the two pulleys with depth meters on a pair of tubes. The tester inserts the sensor into the tube, which is filled with water for good coupling. And the sensors are lowered all the way to the bottom of the pile. Once we reach the bottom, we make sure that both sensors are at the bottom and at the same level, and we start pulling when we get the order to pull. The depth meter shows you exactly where the sensors are at any moment. And you can see on the right bottom the pulses as they arrive from the transmitter to the receiver. When you reach the top of the pile, you can see the results on your screen. The results include the time of the first arrival, the energy, and the wave speed between the tubes. The wave speed is connected to the compressive strength of the concrete. The higher the concrete strength, the higher the wave speed. This is the CHAM method. It's very portable. One person can operate it on site. And it can reach depths of 100 meters and even more. The CHAM, as you see, can do also tomographical testing in 2 and 3 dimensions. The access tubes are arranged like this. If you have only 2, of course, you don't have many choices. 3 tubes, 4 tubes, 5 tubes, and we've seen piles, very large diameter piles that have up to 10 tubes. In the United States, they install 1 tube per average 30 centimeters of diameter. For instance, a 1 meter diameter pile, 3 tubes, 1.5 meter, 5 tubes. In the Far East, China, Vietnam, I don't know about Indonesia, normally they use 4 tubes regardless of the diameter. This is a typical pulse. In the beginning, you see the line is totally flat. This is the period it takes the pulse to travel from the transmitter to the receiver. This is the first arrival time, and this is the pulse, when all the waves start arriving in the receiver. As we said, we have the results include the FET, first arrival time, very important, relative energy, decibels, apparent wave speed in meters per second, and of course, the waterfall presentation. On the left, you see a typical graphic presentation of a pile that has quite a serious defect at this depth, at 3.5 meters. You see longer FET travel time, lower energy, and the waterfall presentation that here is nice and healthy doesn't appear here. The gray becomes totally white. As I said, the CHAM can also produce tomography. When we pull the sensors, not at the same level, but at diagonal directions. Here we must use 2 depth meters to let the system know where each of the sensors is located. Here are the results. We have several methods to analyze the results. And here you can see not only at which depth the defect is, but also the horizontal extent of the defect. You see here that it's closer to the right-hand tube. Tubes, we can also perform 3-dimensional tomography that can show you the pile in space. You can see on the right-hand side of the screen. And you can have horizontal and vertical cross-sections and evaluate the strengths of each of these cross-sections. Now let's put some order in the definitions of anomalies, flaws, and defects, because many engineers mix between these terms, and this misunderstanding can become very expensive. Anomaly is any irregular feature in the entity non-destructive testing results. It can be due to a number of factors. Testing instrument. If the testing instrument is one with a lot of internal noise, you can have anomalies. Means used. If the tubes are not filled totally to the top with water, it affects the results and you have an anomaly. Or if you have plastic tubes that debond or separate from the concrete, you can have an anomaly. Surrounding soil, we saw in the PET test how soil affects the results. And of course, an anomaly can be caused by an actual flaw or defect. So the 3 first factors have nothing to do with the pile itself. Number 4 has. A flow. A flow is any deviation from the planned shape or composition of the pile which does not necessarily detract from the pile's performance. For instance, a bulge, larger cross-section, is normally doesn't cause any negative effects on the pile, but it's still a flow. It is deviation from the planned shape. A defect, a flow that because of either size or location may affect the pile's capacity or durability. Now, who is in charge of these definitions? The testing laboratory is responsible for reporting anomalies and assessing which anomaly comprises a flow. So the testing laboratory is your eyes on site. They see what's going on and they can investigate and inquire the site people if there were any events during the construction of any given pile. If the testing laboratory determines that the anomaly is a flow, it is brought up to the geotechnical engineer and the structural engineer. And they assess the results and determine which flow comprises a defect. Now, a pile with a defect doesn't mean that you have to throw it out of the window immediately, of course, if you can. A pile with a defect can be repaired or can be left as is, depending on the situation. That's the reason that why two engineers together have determined that the pile has a defect and what to do about it. Here is a graph, it's called the Venn diagram, that shows you that some anomalies can be flows and some of the flows can be defects. It also shows you that some flows do not produce anomalies, even some defects, which means that all testing systems and all testing methods have some drawbacks. Another subject, inclination testing, the bit. Apparently all piling specifications demand that the deviation of the pile from the vertical will not exceed any given value. For instance, Federal Highway Administration in America, they allow 20 millimeters per meter deviation from the vertical. The bit borehole inclination tester is the tool for checking the verticality of piles. You can attach it to the top of the drilling bucket here. It is totally waterproof to a depth of 150 meters below the mud level, and it can determine with the bucket used as a centralizer the verticality of the pile. Here you see the scheme. Number one is the instrument located inside the cable reel. Number two is the sensor located on the drilling bucket. Number three is the wireless depth meter. And number four is the data logger that is normally just any Android smartphone. How is the test made? In this case, we'll see how the instrument can be lowered inside the access tubes that are located in the pile for chum testing. You don't need any special tubes. And unlike normal inclinometer tubes, they don't have to be special grooved plastic tubes. You can use normal 50 millimeter steel tubes. With these piles, we want to know the deviation. Here is our centralizer lowered into the access tube, the 50 millimeter access tube. On top of the tube, you can see the depth meter. This is the cable reel with the instrument inside. It is connected by wireless to the depth meter and to the phone. We lower it in stages. We make a stop every few meters for stabilization of the reading. When we reach the bottom, we pull it back and we stop at the same stations. Once we reach back the top of the pile, we can see on the screen if we have any test error. We can see the profile of the pile in any direction, and if it deviates from the allowable deviation, we can see immediately. This test can be repeated for all tubes, and the average produces the pile deviation from the vertical. This is a second pile wall with the piles cutting into each other, where the inclination is much more important than in foundation piles. The same bit can be used also for geophysical testing, where the inclination is important. Here you see the output in the report. You see a top view. It shows you in which direction the pile is deviating and the amount of the deviation. Here is a side view. The green area is the area allowed by the specifications, for instance, 2%. So if you have an 18-meter pile, the allowable deviation at the bottom is 36 centimeters. And we see that this pile is okay. Now, to the last testing method, where we want to test unknown depths of piles, parallel seismic method. If we have to check the foundations of a very old building where we don't have any record, and we must know the exact depths of the foundations. For instance, if we have to excavate under the building or near the building, we use the PSI, parallel seismic method. Here is an example. We have a bridge, old bridge, with foundations, of course. We don't know anything about the depths of the foundation. This is our instrument. It has several components. The instrument itself is powered by the USB cable from the computer. It doesn't need any internal battery. We connect to the instrument the cable reel with the hydrophone, the special sensor. We have a depth meter, which we put on the access tube. And here is our hammer with an impact switch, which is also connected to the instrument. if we hit the top of the structure and we don't know what kind of foundation we have, the waves we produce with the hammer blow go down in the foundation and sideways to the access tube that we drill close to the foundation. The hydrophone is lowered by stages in the tube, and all the time we keep hitting. And this is the result. On the left is the depth scale, and on the right hand, the time of the first arrival. We see that up to a value of depth of 18 point something meters, the first arrival lines have a straight line, and below that we see a break, because in the upper part the wave goes through the pile, in this case a concrete pile with a higher speed, and in the lower one the waves continue to travel from the pile in the ground where the wave speed is much lower. Conclusions. I hope that by now you will agree with me that in piles, defects may be and therefore will occur. Innovation in piling is usually accompanied by an increased defect rate. It takes time for the contractors to master the new innovation, the new construction method, and of course for engineers to write the correct specifications. Integrity testing techniques are used to discover defects before they can cause any damage. The word before is accented here. After they cause the damage, it's a little too late. Current integrity testing techniques can discover most important defects. And I accented the words most, not all, and important. There may be some defects that are important and we cannot discover them because they are out of the range of the system. It is very important to know the capabilities and limitations of the method we are using. And it's very important to test all the piles. This is a short commercial from the last webinar, and I think that the sale is still in force. Gadi, is it?
Yes,
Yes.
still in force.
So please be in touch with Zulfkri if you think this is interesting for you. Thank you for listening. And do we have any questions from the audience?
Maybe you can see the question and answer room. Untuk semua peserta, silakan sampaikan pertanyaannya di ruangan question and answer Q&A di sebelah kanan dari layar monitor kita.
יש כרגע רק 3 שאלות.
Mr. Joram, can you see the first question is from Mr. Rudi Hermawan?
When?
Just a moment. The question is necessary if one project with 12 stories using 2 test pilings as PDA tests with Kentledge, or adequate with only 1 test piling. Well, first of all, I think that a building with 12 stories needs a very thorough integrity testing program if it's founded on piles. And of course, that test loading can add a lot of information. Of course, if you can afford testing with Kentledge or with any other reaction method like ground anchors or anchor piles, doesn't have to be Kentledge always. Static flow test is the best. PDA testing, pile dynamic analysis is the second best. A question by Mr. Muhammad Rahmani. It's not clear how to check in PIT tool if the pile is crack or poor. This is a very good question. This is one of the drawbacks of the method. The method doesn't give you the name or the character of the flow. It shows you if you have a lower or higher impedance. So a crack or poor concrete, both will give you a reflection of the same form. So you can't know. You know that you have a defect or a flow at this level. Another drawback is that if you have a serious flow, you cannot know anything about what is happening below this flow. So only the uppermost one is discoverable. Another question by Mr. Rahmani. Did you guys open training? Well, we can provide training. You see the presentation we had today is part of our training program. And of course, we can make training program as necessary. Another question. Where is it?
Can I measure? Can I measure?
Can I measure the density of pile material using this tool? This tool can help you measure the density indirectly. So you can check the wave speed or the average wave speed in the pile, and the wave speed is connected with the strength, compressive strength of the pile, and with the modulus of elasticity. Of course, if the wave speed is low, it probably shows that the density is also low and the concrete is poor. But you cannot measure it directly. Next question. What method is the most accurate in loading test, pile, and low cost? It depends. You know, once I was in India, and I don't know how today, but 20 years ago, manpower in India was very low cost. And during one night, they built a beautiful Kentledge of 300 tons by carrying on their backs sandbags. So it depends. Kentledge can be very expensive and can be very low cost. Any more?
No.
Okay, that's all. I must say thank you again for attending this webinar today. And please get in touch with us if you have any more questions.
Yes, another question. Another question, how many testing for PDA, each pile or group?
Another question, how many testing?
Oh, that depends on many factors. Of course, if you have specifications, you have to follow the specification. If you don't have, it depends on the situation. You know, in principle, I don't like load testing at all. You know why? Because if you have to perform many load tests on piles, it means that you're very ignorant. A good engineer, if you have good soil tests and good theory and good analysis tools like Plaxis, for instance, yes, can calculate the load carrying capacity of the pile fairly accurately. So load testing in this case is justified only for large projects and also only to corroborate the results of your analysis. You know, structural engineers, they design high-rise buildings. Do they perform load tests on the whole structure? No. They have full confidence in their calculations.
Mungkin ada yang mau bertanya langsung, bisa enough, maybe someone who like to ask directly, maybe give opportunity to speak, maybe. Saya tunggu 1 menit ini, kalau ada yang mau tanya silakan, atau di Q&A. How many time to test is using spoon pile or the same pile? Is the question from Mr. Cahyo.
How many time to test is using span pile for the same pile? I must admit that I don't understand the question. Can you elaborate maybe, Zulfkri?
Pak Cahyo, maybe
if you check it with the gentleman, send me the question and I'll answer you today later by email.
Yeah, mungkin maybe the question is about the frequency of testing is the same pile with the non-destructive testing equipment.
Frequency of testing.
Yes, I mean frequency of testing. I mean how many taking the data hit the pile, maybe for the PIT.
Well, how many blows for each test?
Yeah, for example, if they use PIT, how many times they use hammer to get the good data?
This is a very good question, and it depends on many factors. If the file is not too long and the top is well prepared, a few blows, 3, 4, 5 blows will be enough. If they show you a nice pattern with a very clear toe reflection. Sometimes piles that are very deep and the top is not very well prepared. In this case, just a moment. Okay. If the going is rough and you get results that are not very nice and it's difficult to find the toe reflection, you have to apply many blows. It's easy. And the system averages all your blows and you see the average in a thick line at any stage. And if it begins to show some toe reflection, you can sometimes collect 50 or 60 blows, which is not very difficult. It takes you half a minute or 1 minute to collect 50 blows. What you do, you move around on the top of the pile with your sensor and hammer and hit. You try different spots. And sometimes not all spots give you a good result. You have to keep trying. That's a question of experience. It takes some time. But it's always better to test more than to test less.
Mr. Joram also have a question about seismic parallel testing. Is it possible to test the pile with the peer head with the seismic parallel?
A pile with a cap on top?
Yes, pile cap. I mean,
pile cap, or even grade beams or some superstructure.
Yes.
Well, in most cases, it's possible, but it doesn't produce optimal results. The best results are produced when you have a clean access to the head. As I mentioned before, you have to try different spots on the head. Once you have a pile cap, especially if the pile cap is very thick and rigid, in some cases, you can try and test below the cap. And by cutting a groove into the side of the pile and hitting below the cap. But again, once you send a wave down in the pile, you also at the same time send the wave up to the cap, which means that you got a very noisy result. And then it's difficult to distinguish between the good reflection and the poor reflections, or the noise.
Thank you for your question.
This one?
How many piles? Yeah, question by Rahman Yusuf. How many piles to test on a project? Are there any standard conditions? As I said before, it depends on the specifications. But since the PET, or the low strain impact testing, is so quick and so inexpensive, I always recommend to test all the piles. Can you test the correctness of the tool to the pile? First use it to the column for test about crack. A question by Muhammad Rahmani. Well, you can test the tool on a column. You can test it on a beam. Sometimes you have precast beams lying on the ground. You can test them, and you can calibrate your equipment accordingly. Okay, any more?
I think no other question.
Okay, listen, if you get more questions from the audience,
yes,
please direct them to me. I'll be very glad to answer all the questions.
Yeah,
especially the good ones.
Yeah, I will try to get it. Usually some of them will send me the question. I will send to you. Teman-teman semuanya, biasanya memang kami mengumpulkan pertanyaan-pertanyaan. Kalau tipsnya ada yang memang ada kasus, silahkan kirim ke saya. Nanti di WhatsApp ya. Nanti kita akan jawab tertulis. Terima kasih atas partisipasinya di webinar kelima Testindo bekerjasama dengan Unsiah Universitas Kuliah di Aceh. Semoga makin maju Aceh. Mr. Joram Amir, maybe the closing statement from you.
Okay, Zulfkri.
Yeah.
Thank you for arranging this webinar. It was a pleasure.
Yeah, you're welcome, Mr. Joram. Pak Surya, maybe from Unsia, maybe have closing statement, maybe Pak Surya.
Oh yeah. Wait. Okay. Thank you very much, Mr. Joram, Mr. Zulfkri, and Testindo for present the webinars today. I think some new information about how to test the foundation is we adopt today. Maybe we can use it in next projects or another projects in Aceh. Thank you very much for your information and knowledge.
Terima kasih Pak Surya. Terima kasih semua ya. Dengan ini kita tutup acara webinar kita. Alhamdulillah, semoga bermanfaat buat semuanya. Mr. Joram, enough. Thank you for everything. Pak Surya, semuanya saya izin live dulu. Bye bye. Assalamualaikum.
Bye.
It was my pleasure. Bye bye.